So, good morning, students. So, today our topic of discussion would be full wave rectifiers. Okay. So, in the previous lecture, we have seen a half wave rectifier. Okay. So, let me draw a simple block diagram of the half wave rectifier. So, if this is my half wave rectifier, okay. So, if a sinusoid is given as an input in this fashion, okay, so what is the output of my half wave rectifier? The positive half cycle of the input is passed through as it is, whereas the negative half is completely nullified. Okay, so and this pattern repeats. Okay, so this is nothing but V out. Okay, so this is aptly named as half wave rectifier because only one of the halves, okay, so in this case the positive halves is let through and the other half, the negative half, is completely nullified. Okay, so that is half wave rectifier. Now today's topic of discussion would be full wave rectifier. So let us see what a full wave rectifier would be in a block diagram. Okay, so full wave rectifier, okay, if this is my input, suppose this is my input in this fashion. Okay, so let me label this V in. Okay, my output would be something like this. Okay, so it lets the positive half cycle through and also it would let the negative half cycle through. Okay, but it wouldn't let the negative half cycle of the input through as it is. Okay, it would invert the negative half cycle as well. Okay, so the negative half cycle is inverted as well and passed. Okay, so now, okay, so this keeps on repeating. Okay, so this type of output is called as full wave rectified output. Now if you remember, for half wave rectifier, okay, we derived three important properties. Okay, one is VDC of the rectified output. Okay, and the second one is VRMS of the rectified output, and the third one is the ripple factor. Okay, so for the full wave rectified output, okay, I expect you guys to come up with these three. Okay, I already gave you detailed explanation. The calculus and the algebra that is involved in this calculation has already been explained in detail for half wave rectifier. So I expect you to come up with these three properties for full wave rectified output. Okay, so that would be one of your assignments for the upcoming class. Okay, right, so now uh, let us look at the full wave rectifier circuit. Okay, so this is how a full wave rectifier circuit looks like. Okay, so the thing that you see, the coils part, is nothing but okay, so this is nothing but a transformer. Okay, so this is usually we use a step down transformer. Okay, in particular this transformer is called center tap transformer. Okay, so it is called center tap transformer. I think as the name indicates, okay, this is called the primary winding of the transformer. Okay, and of course this would be called the secondary winding of the transformer. Okay, so if you see in the secondary winding there is a tap at the center. Okay, so that is why this is called the center tap transformer. So what this step down center tap transformer does is, so we all know that all our home sockets we get 230 volts AC at 50 hertz. Okay, so what this does is it steps down the voltage usually to 15 volts AC, especially if it is a step down transformer, and especially if it is center tap. Okay, if it is a center tap step down transformer, what it does is, okay, so let me copy paste this again. Okay, so what the center tap transformer does is nothing but, okay, so if the input to the center tap if the input to the primary winding is something like this. Okay, so vi, if the input to the primary winding, so vi is nothing but the input to the primary winding. If the input to the primary winding is in this fashion, what the center tap transformer does is it creates two copies of vs. Okay, so this is vs and this is also vs. Okay, so between these 2 points, so we have one vs, and between these 2 points we have another vs. So this is what especially a center tap transformer does. Okay, so now, so given a vi, now what do we have at the secondary of the center tap transformer? So we have two vs's. Okay, so again the shape wouldn't change, the transformer never affects the shape. Okay, the shape is not affected. You see, the input is a sinusoid, the output is also sinusoid. Also, of course, because if it is a step down transformer, it might affect the amplitude. Okay, but it wouldn't change the shape or phase shift or any such properties of the sinusoid. Okay, so um, so what is happening at the center trap transformer here? So at the primary winding, if we have a signal like this, okay, so at the secondary winding now we have two sources, one vs here and another vs here. Okay, so that is the beauty of this center tap transformer. Okay, right, now let us try to analyze what is happening. Suppose now, like always, all these discussions okay, go about which one of these diodes is forward biased and which one of these diodes is reverse biased. Okay, right, now let us see. Now let us go halfwise. So in the time interval between 0 to t by 2, so our vi is positive. Okay, so that means because this is vs, okay, so vs also will be positive, and this is vs here, this vs will also be positive. But you have to be very careful here, because in the bottom, okay, the negative terminal of vs is connected to this diode d2, whereas in the top the positive terminal of vs is connected to diode d1. So I am making one important conclusion here. See what is happening when va is greater than 0, that is in the positive half cycle. Okay, that is in the positive half cycle. What is happening? vs is also greater than 0, but because vs's positive terminal is connected to d1, your d1 is forward biased, and when it is forward biased we replace it with short circuit. Similarly, when va is greater than 0, vs is also greater than 0, but if you look at the bottom, the negative terminal of vs is connected to d2. So when, even though vs is greater than 0, since negative terminal is connected to d2, okay, so the p side of d2, okay, so the p side of d2 over here is a negative value. Okay, so that is why this becomes reverse biased. Okay, so diode d2 becomes reverse bias, and in reverse bias we replace it with an open circuit. Now we, because this is open circuited now, okay, so there is no current flow from the bottom. Okay, only this portion of the circuit is on. Okay, so when vi is greater than 0, okay, so v out is nothing but voltage drop across this resistor, that would be nothing but vs. Okay, so what is happening in positive half cycle of the input? Okay, so when vi is greater than 0, v naught is equal to vs. Okay, remember vi is the input to the primary winding of the transformer. Okay, and at the secondary we have the vs. Okay, this is vs, and v out is the output that we are finally interested in. Okay, so when va is greater than 0, v naught is equal to vs. Okay, right, now let us see what would happen. Okay, so let me put this even further down. Okay, so let us see what would happen in the negative half cycle. Okay, so like I said, okay, so if this is vi, okay, like we discussed earlier, because of the nature of the center trap transformer, this is vs and this is vs2. Okay, now when vi is greater than 0, what is v naught? V naught is nothing but equal to vs. Okay, now we go to the, sorry for that, we go to the negative half cycle of the input, that is when vi is less than 0. Okay, so uh, this is vi, so when it is less than 0, that is we are worried about the negative half. Okay, when vi is less than 0, what would happen? Because this is now a negative value, d1 is switched off. Okay, so this is a negative value. What is happening when it is negative? Okay, the p side of d1, so let it be p1, okay, is a negative value. When it is a negative value, okay, what happens to d1? D1 is reverse bias, so when it is reverse biased, we simply open it. Okay, right. Now because this D2 is connected to the negative terminal of Vs, okay, when Vs is going in the negative direction, what the P side, okay, P, this will be looking at a net positive voltage. Why? Because, okay, because this is already connected to the negative terminal, and when this voltage is negative going, minus into minus becomes plus. So this terminal, that is the P side of the diode D2, sees a net positive voltage, so diode D2 is on. So when vi is less than 0, so diode d2 is on. Okay, when that is, it is nothing but forward biased. When it is on, it is nothing but we replace it with short circuit. Okay, so what happens? So this path is now broken because this is open circuited. Okay, so this path is open, whereas this is closed. Now this is short circuited. Okay, what happens now is, so now there is a net current flow through this direction. Remember, because this is negative terminal connected to d2, and a net negative, the negative half cycle is flowing, we see a net positive voltage. Okay, so this current flows through v naught. Okay, this current flows through, sorry, the resistor r, and v naught will be nothing but equal to minus of minus vs, that is nothing but equal to vs. Okay, now if we put these two together, okay, so when vi is greater than 0, what do we have? V naught is equal to vs. Okay, when vi is less than 0, what do we have? V naught is equal to vs. Okay, so if we plot those waveforms, what do we have? If this is uh, vi, okay, and this is the secondary winding, this is vs. Okay, so what is my v out? Okay, so this is vs. So what do, when vi is greater than 0, okay, so v naught is equal to vs. Okay, and when vi, even when vi is less than 0, v naught is a positive value. And what is that positive value? That positive value is nothing but equal to vs. Okay, so this goes on. So this is nothing but a full wave rectified output. Okay, right. So this type of rectifier is called center tapped full wave rectifier, because we use a center tap transformer over here. This is called a center tapped full wave rectifier. Okay, right, but usually these center tapped transformers are a bit costly. Okay, so that is why we try and avoid usage of such costly hardware. We try to use the normal transformers to achieve full wave rectification. Okay, so that leads us to the next topic, which is called as bridge rectifier. So the circuit diagram that you are seeing below is that of a bridge rectifier. Of course, this is also a full wave rectifier. This is also called bridge full wave rectifier, okay, in some textbooks. Okay, right. So like you see here, this is a normal transformer. You don't have any center tap over here. Okay, a normal transformer with a primary winding here and a secondary winding here. Okay, there is no center tap over here like you see, but over here we have four diodes versus two diodes, okay, that you used in the center tap transformer case. Okay, so here we'll be using diodes extra compared to your two diodes extra compared to your center tap transformer full wave rectifier. Okay, right. Now let us try and analyze. Okay, so let me take a copy of this. Okay, so let me take a copy of this. Yeah. Okay, now so so if this is my input Vi to the primary winding of the transistor, okay, secondary winding like we discussed earlier, okay, depending on these n1 n2, okay, so that is nothing but number of turns. N1 is nothing but number of turns. Depending on the number of turns in primary and secondary, okay, we get either step up or step down. Okay, so but we usually use a step down transformer. Okay, so at the secondary winding, what do we have? We have a Vs. Okay, remember the shape doesn't change, only the amplitude changes. Okay, so at the secondary now we have Vs. Now let us try to understand the nature of Vs. Okay, right. Again, we divide the analysis into two parts. One in which, okay, sorry, the first one is during which Va is greater than 0. Okay, so that is in the positive half cycle. Okay, now let us do the analysis for positive half cycle. So when Va is greater than 0, Vs is also greater than 0. So I will draw some important conclusions. See, so in the secondary, I can say that when Va is greater than 0, this node is the most positive node and this node is the most negative node. Okay, in the positive half cycle, when Va is greater than 0, okay, so when Vi is greater than 0, what is my conclusion? So this node, okay, is the most positive node in the entire circuit because this is connected to negative. Okay, so this node is the most negative node in the entire circuit. Okay, so with that in mind, let us now analyze which one of these diodes is forward biased and reverse biased. So let us go diode wise. So suppose D1. Okay, so what is happening to D1? Because the P side of D1 is connected to most positive node. Okay, so that means P1 can only be greater than N1. Why? Because we know that this node is the most positive node in the circuit. Of course, only when Va is greater than 0. So D1 P1 will be greater than N1. That means D1 is forward bias. So D1 is forward biased. Okay, right. Now let us try to go to D3. Okay, so what is D3 doing? D3 is N. This is nothing but N side of D3 is connected to most positive node. Okay, so that is nothing but N3 is, I can draw the conclusion that N3 is greater than P3. When N is greater than P, I can say that diode D3 is reverse biased. Okay, now let us go to D2. Okay, so what is D2? So what is D2 saying? Okay, so here this is the most negative node. Okay, so that is nothing but N2. Okay, N2 is a very negative value in the entire circuit, whereas P2 is connected to ground. That means I can draw the conclusion that P2 is greater than N2. Why? Because here the P side of D2 is connected to ground, whereas N side is connected to the most negative node. That means P2 will be greater than N2. That is nothing but diode D2 will be forward biased. Okay. Similarly, okay, so let us now analyze D4. Okay, so in D4 the P side, okay, is connected to the most negative node. Okay, so that means P4, the P side will be less than N side. Okay, will all, because P side is connected to the most negative node, so P side will always be less than N side. That means D4 will be reverse biased. Now what are the two diodes that are on? Okay, diode D1 is on and diode D2 is on. Okay, so these will be replaced by short circuits. Okay, and these two will be replaced by open circuits. Okay, now if you see the arrows over here, okay, because a diode also allows a current only in P to N direction, isn't it? So such type of understanding will also help us here. Okay, so D1 is forward bias, so this is open because D3 is reverse bias, this is open. D4 is also reverse bias, so this is open. Okay, so this is closed and this is closed. So what happens to the current? Okay, now the current flows through diode via this resistor R and through this diode R2. Okay, so because the current is traveling in this direction, okay, so these will be the plus and negative terminals of the R. Okay, so this is where we take the output V0. Okay, so when Vi is greater than 0, okay, what is V0? V0 is equal to Vs. Okay, so V0 will be equal to whatever is the Vs over here. Okay, in the positive half cycle. Okay, that is nothing but this one. Okay, when Vi is greater than 0, this passes through. Okay, now let us analyze the second half. Okay, let us analyze the second half. Okay, right. Now we have done the analysis for the case when Va is greater than 0. What did we get? V0 as V0 is equal to Vs. Okay, right. Now let us analyze the case for Vi less than 0. So that is the input to the primary winding is negative half cycle now. So you are dealing with this. Okay, so we know that Vs will also be similar to Vi but only with amplitudes changed. Okay, so in the negative half cycle what is happening is, I will draw another conclusion here. In the negative half cycle what is happening is this node, okay, because this is minus, this is the most positive node, this becomes the most positive node in the circuit. And similarly because this is negative going, okay, of course, because this is negative going, this is nothing but most negative node in the entire circuit. Okay, so with those two conclusions, now let us try and understand which region of operation each diode is in. Okay, now let us start with diode D1. Okay, so the P side of D1 is connected to most negative node. That means of course P4 will be less than N4. Okay, that means diode D1 will be reverse biased. That means it will be open circuited. Okay, now let us go to D3. Okay, what is happening to D3? Your N side of D3 is connected to most negative voltage and P is connected to ground. Okay, so that means P3 is of course 0. Ground means 0. It will be greater than a negative voltage. So that means P3 is greater than N3. That means diode D3 is forward bias. So it will be replaced by a short circuit. Okay, now let us analyze D2. Okay, so in D2 what do we have? The N side of D2 is most positive. Okay, so N2 is most positive, that means N2 will be greater than P2, so that means diode D2 will be reverse biased and it will be open circuited. Okay, now let us discuss the condition of diode D4. Okay, so here you see the P side of diode D4 is most positive, that means P4 will of course be greater than N4. That means if P is greater than N, diode is forward biased, so it will be short circuited. So here we have D3 and D4 on. Okay, so that is nothing but D3 is on, D4 is on, whereas D2 and D1 are reverse bias, so they are off. Okay, now what will happen, how would the current flow? The current would now pass from D4 through this resistor R and it will pass through D3, so that will be how the current will be flowing. Okay, right, see, remember the current direction in the previous case was in this fashion. Even in this case the current is flowing in the same fashion. Okay, so the voltage V0 will be equal to Vs even in this case. See, the voltage, the V0 that was developed in the positive half cycle was plus here, negative here through D1 and D2. In the negative half cycle, the current is flowing from D4 to D3, so the current is flowing in the same direction. That is nothing but V0 will have the same polarity either in positive half cycle or in negative half cycle. Okay, V0 will be having the same polarity and that will be equal to Vs. Okay, in positive half cycle V0 will be equal to Vs, and in negative half cycle V0 will of course be equal to Vs. So what do we have? So if Vi is doing something like this, okay, this is Vi, okay, that is input to the primary winding of the transformer. This is Vs. Okay, what is V0 doing? Okay, this is Vs secondary winding. What is V0 doing? V0 is the output of the full wave rectifier. So in both half cycles, okay, V0 is equal to a positive value of Vs. So that is why, okay, this is called a full wave rectifier. Okay, I hope you could understand both the circuits. Okay, so the first one was the center tap transformer. Okay, center tapped full wave rectifier, and the second one is bridge rectifier. Okay, so these are the two important topics, and I already gave you the assignment. Okay, for a full wave rectifier output, okay, you have to find out VDC, VRMS and ripple factor. Okay, so it's simple calculus. I am sure most of you can finish it on your own. Okay, if you have any doubts regarding full wave rectifier, please do ping me on my personal window. Okay, thank you.